Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Florian Debras with us today. Hey, Florian.
Hey, Frank.
How are you today?
Well, I'm great. It's the first day since the beginning of the summer when we actually have a bit of sun. So,
so where are you at?
I'm in my office in Toulouse, in south of France.
Toulouse. Okay.
Yeah, and yeah, we had the last month's raining, which never happens in July, but happened today.
Yeah.
What about you? How's it in Phoenix today?
Phoenix, we are somewhat a little bit like you. We're unusually a little cloudy today, a little cool. So we got a little rain last night. So yeah, it's not the usual 43C, 44C in Phoenix. So we're down a little bit. We'll hit 38 today, 39. But it's generally clouded over, so we don't have that big sun banging down on us, which we're grateful for. But I think you're probably a little more grateful for the sun actually coming out in Toulouse. So
yes, definitely.
And with the sun out, maybe that'll give you a chance to ride that item that's on your shirt there. I love that logo, your bicycle. Do you ride? Do you bicycle?
Yeah, I ride to work. Basically, it's 10 kilometers, so it's a bit of a distance, but it's pretty nice in Toulouse. We have nice bicycle, lanes. It's all right.
Have you ever bicycled over part of the world or have ambitions to bicycle across the world?
Yeah, actually, I went through Africa, South and Eastern Africa for 5,000 kilometers.
Wow.
So, I did have a nice trip.
Very cool. How long did that take?
It was about 3 months and a half.
3.5 months. Very nice.
It was really nice, and it was cycling under 35 degrees C as well. So it was.
Did you go solo or did you go in a group or?
We were just the two of us.
Two. Okay.
Which we had just like a flight for getting there, a flight for getting back, but nothing planned in the middle. So that was fun.
Very nice. Very nice. Open itinerary on travel is always nice, particularly on a bicycle. Bicycle travel is lovely. Very cool. Cool. Florian, what do you like to do for research?
Well, I specialized in the study of exoplanets and planets mainly. I began with Jupiter stuff. So really trying to understand what's inside this giant planet. And I also worked on the atmospheres of hot Jupiters when I was in England, which was more numerical than when I did on the Jupiter study. And then I kept in the field of exoplanets, and I've also studied a bit of migration of exoplanets in the past few years. We just published something on the eccentricity last year, and yeah, so that was fun. And finally, which what I'm doing at the moment, and which I spend my day on, because it's the end of the day here, is trying to observe the atmosphere of exoplanets. So I'm working with Spirou at Hawaii. Yeah, and it's yeah, that's basically my main interests.
Lovely, very cool. And that is going to bring us to this super lovely APJ letter on superadiabaticity in Jupiter and giant planet interiors. And Florian, take us away.
Yes. Okay. So the origin of this paper is Juno, really. So when the satellite arrived around Jupiter, it changed a lot of our understanding of Jupiter, and there's a lot of lovely things about the observations. And what we realized is that the density profile of this planet was not compatible with what we thought it was before Juno arrived. And something really strange is that usually what we say in the modeling of giant planets is that the least dense profile is the adiabatic profile. You cannot be less dense than the adiabat, because, well, basically, if you're less dense, then you're going to be unstable and you're going to be back to the same density structure.
Right.
Actually, if you take the external adiabatic condition and you push it to the interior, you will notice that you cannot match the gravity field that Juno observed.
Okay.
And so that was an issue.
Okay.
And so what we have tried to show in this letter is that actually this condition that you cannot be less dense than the adiabatic profile is only available on a very local scale. And it's called the usual Schwarzschild-Ledoux criterion, which is well known. But if you go on a global scale, and this is well basically said in the abstract, then you can really overcome this criterion because there is no global criterion for the Ledoux instability, let's say.
Okay.
And the whole point of this article is to go through this idea, which basically change a bit what we can predict for Jupiter and as well for extrasolar giant planets.
Yeah.
So yeah, so if we go through it, so the introduction is really, yeah, we wanted to just put the ideas back together to what we knew about Jupiter before Juno arrived, how the vision of Jupiter changed with Juno. And I think one of the major articles is in the first paragraph is the Watt et al. 2017, where they really showed that there might be some weird condition like a diluted core in Jupiter and stuff like that. And yeah, expand on the fact that there is a trouble with the density profile, which has to be less dense at the outer adiabatic profile. And so this is the whole point of
right
of the letter.
Cool.
Very
good.
Yeah, so yeah, that's basically just a small introduction about that. So if you go down on that, we'll take it to well, just the definition of
that would be good.
Yeah, no, it's the definition of the usual equations for the density and temperature profile in a giant planet. So what we see if you well, yeah, let's take a look at equation 1 because it's going to be just basically what we have to, the kind of ideas we need to have in mind. And so we're going to speak a lot about what is called the temperature gradient. And you'll see that basically in an adiabatic condition, so in a convective medium, which can be, well, you can say that adiabatic is isentrope in Jupiter. Then you have a condition on the adiabatic temperature gradient and the condition in equation 2 on the adiabatic density gradient. And so the real important thing to notice is, as I said, we cannot have a decrease of the density gradient with depth, which is a problem because that's what Juno requires, to have a decrease of this density gradient. And so notably, if you're not convective, you could be conductive, but this has a lot of implication on the history of Jupiter. And there's a lot of conditions that make it quite hard to reconcile with what we know about the planet. But what you can have is what we called basically inefficient convection, which is a kind of a double diffusive instability. And so you have a competition between the diffusion of heat through your convective cells and the diffusion of molecules, of particles. And this leads either to so equation 7 or 8, which are the definition of fingering convection or semi-convection. So fingering convection is actually quite nice because it's been studied from the ocean community originally.
Right.
And it's been applied in the past, well, 3 or 4 decades in the astrophysics, but it was really, yeah, made in the ocean usually, where you have some gradient of the salt composition in the oceans.
Right.
So yeah, so I won't talk about fingering convection anymore, but in Jupiter, there can be a place of semi-convection where basically the molecular weight increases with depth. So what that means is that you get heavier and heavier material as you go down in Jupiter.
I have one question.
Yes, sure.
What is the what is in equation 1 and 2? What does the subscript CTE mean?
Constant. Sorry.
Constant.
Yeah.
Got it.
Yeah, it basically states that if you are adiabatic, then convection is going to homogenize the molecular weight.
Right.
So your medium is going to be at constant composition.
Got
it. If you want to be less dense than the adiabat, you need to change the composition. But if you change the composition, you get to equation 7 and 8. And what they say is that you are more dense than the adiabat. That's the first inequality. Yeah. So that's really the starting point of like the common misconception that you cannot be less dense than the adiabat. Because you cannot be locally less dense than the adiabat. This is what this equation shows, but I'm going to show in the rest of the articles. And in a global way, you can be less dense than the adiabat.
Okay, good.
That's really the idea.
I'm with you.
Yes, cool. So yeah, so there's a lot of interesting thermodynamic quantities that can help you to be either more or less dense, but globally, the real important thing is what I just said. You cannot be locally less dense than the adiabat, because if you are, then you're going to be unstable and you're going to go back to the adiabat.
Right, and then you will be.
Exactly.
That you go back to there. Very cool. Okay.
So yeah, so this is where basically, so we knew that with Jupyter there was a problem with this adiabat, but at the same time, people always thought that you cannot be less than the adiabat. And so we had this naive picture that you can see on figure 1. It's a very simple cartoon, and all of this paper is basically just simple cartoons to explain the science. When I was in undergrad, my math teacher always said that doing science is having a proper reasoning on a false drawing. So let's say that's a false drawing.
I haven't heard that one yet. That's very good.
So yeah, so that's a false drawing. So basically, very simple enough. What we say that you are, so at the left part of this plot, so you have density as a function of pressure. The left part of the plot is the exterior of Jupiter, and the right part is the interior of the planet. Okay. And so what we say is that we follow the convective medium, so S is equal to S0, the black curve, until some pressure, which we call PI, sorry, where you have some non-convective effect that start to develop.
Yep.
Non-convective effect, as I said, they must lead to a higher density initially than the adiabat, or you would not be stable. And so this leads to this red curve being above the black curve.
Yes.
But eventually, when you go deeper, you see that the red curve can cross the black curve. So, until you get back to a new inner entropy, which is not S0 anymore, but which is called SF. And this inner entropy is necessarily higher than the outer entropy for this to happen.
Yep.
So yeah, so very, very simple idea. So the question now is, can we go through the math and to the numerics as well, and try to see whether this is possible actually in nature. Okay. And I think it goes to the next equation, or do we have something in middle? Yeah, so we yes, exactly. So I think the most important is equation 12. Where we go there, which is just under. Okay. So yeah, so this equation 12, it really expresses the condition of the local stability, as well as so the condition for the local stability. Yes. And basically you just have in equation 11 the definition of the density gradient as a function of the thermodynamic quantity. So gamma is the adiabatic index, and yes, and all the other quantities are quite obvious. And so what we say here is that if you fulfill this condition somewhere in Jupiter, what happens is that your density gradients will become flatter than the adiabatic density gradient in your planet. Okay. And this is making no assumption on the equation of state. So you're not saying it's a perfect gas or an ideal gas or something like that. Good. Good. So as you might expect, Jupiter is not an ideal gas. Yep. And so the question is, do we fulfill this quantity somewhere in Jupiter? Yeah. And so there could be two ways to fulfill it. Either you have a kind of an extended region where little by little your density gradient gets flatter. Okay. Or you could have a diffusive buffer, so somewhere in the planet, a very stratified region, and which then leads to a much flatter density gradient because the temperature at the end of this buffer is going to be much hotter. Okay. So the entropy. So that's basically the idea. So we have to verify whether this equation, which is really simple, is fulfilled somewhere in Jupiter, and yeah, if it's physical. So if you go to the next figure, I think. Figure 2. And the figure, yeah, figure 2 is just what I said, but it's yeah, you can show it still. It shows this effect that in order to, so yeah, I can explain a little bit. In order for the density gradient to be flatter than the adiabatic density gradient, so the black curve, you either need your big diffusive buffer, where you see that you have initially a very strong density gradient, and then at the end of the density gradient, you're so hot, then your density gradient with pressure is now almost flat for the rest of the planet. Right. Stability. And the second one, what you see is that you have an extended semi-convective region, so what we mentioned in the beginning, and each blue line is the local adiabat. So what we say here is that you always need to be above the local adiabat. That's the Ledoux criterion. But eventually you get under the outer adiabat, which is the black curve.
Yes, right here. Yep.
So yeah, so that's really the idea. So the idea is that if you want to get to a lower density, the proper quantity to think on is the density gradient. And so we are just comparing the density gradient along the real profile of Jupiter with the density gradient of the outer parts of Jupiter. And yes, so that's really the starting point of all this exploration.
Okay, nice.
Thank you. No worries. So yeah, so this paper happened after a former paper where we really derived some internal models for Jupiter. So we had some models to check the value of these quantities. And what's interesting is that, yes, that's no, it's the Debras and Chabrier 2019, the first one which is mentioned.
2019.
Exactly. And the second mention is the Chabrier et al. 2019 and Chabrier and Debras 2021. These ones are the new equation of states that have been derived in the past few years.
Yes.
From the improving in both simulation experiments, like real compression of hydrogen, as well as the improving of the simulation, so quantum molecular dynamics numerically speaking. And one of the big one is the one made by Militzer and Herban in 2013, where they really improved our understanding of the behavior of hydrogen and helium at high pressure, in Jupiter, basically.
Cool.
So yeah, so on this equation 12, as I said, you don't depend on an assumption on the equation of state. So the equation of state we used were these new ones, which are really different from the one we were using, that the community was using in the past 30 years.
Sure. Yes.
So it was it was nice to see the effect, and it's actually it was a bad surprise, let's say, because this equation of states have a different compressibility, which leads to a higher density with depth compared to the previous equation of state. So which was even more incompatible with what Juno observed.
Yeah, some sense went the wrong direction. Yep.
Yeah, exactly. So that's why there's a lot of ink that is flowing on these matters.
Good. Very good.
Yeah, exactly. Yeah, I often say that we were lucky that Jupiter has such a small gravity field in absolute value, because we can do a lot of science. Because if the absolute value of the gravity field, the gravity moment were higher, we could not say anything, basically.
Yeah, right. Very cool. Very cool. All right.
So yeah, so on this figure 3, what we see is we can zoom it on. It's the same figure, but either with pressure or with radius. So the only subtlety is that on the first figure, the pressure, you have the out part of Jupiter on the left and the inner part on the right, whereas it's the opposite for the right figure. But it's exactly the same figure if you.
Yes, interior is over here. Yeah.
So in here, interior is to the right.
Right.
So in our models in 2019, we had a very big semi-convective region. So that's what we advocated for, rather than a diffusive buffer, as I mentioned before. And so our semi-convective region was defined between the two red lines, dashed lines that you see here. So at a few, close to the megabar pressure level. So a million times the Earth's atmospheric pressure here, which is basically the outer skirts of Jupiter. And so in orange, let's start with this one, is the actual density compared to the density of the outer adiabat. And so what you see is that there is a region after the second red dashed line where the density is actually smaller than the density of the outer adiabat. So this is exactly what we advocate for.
Right.
The green curve is exactly this. Sorry, excuse me?
It's a density inversion, right?
Yes, exactly.
Yes.
So the green curve is exactly the same, but when we add the effect of the metal composition, which increase this effect. Because, this is also something of our model. We advocate that the atmosphere of the planet is decoupled from the interior, and so the atmosphere is enriched. But this is something which is still debated in the community. So in either case, you have a decrease of the density with depth, which is interesting.
Yes.
Well, this is at the cost of an increase of the density in the outer parts of Jupiter, but basically it doesn't matter as much.
Right.
And so the blue curve is density gradients, and we've shown that they satisfy exactly the equation 12. So that's basically the difference in equation 12.
Okay.
And it's also shown just for consistency, because basically what you see here is that when you have a maximum in density, you have a null density gradient. And when you have an extremum in the density gradient, you have a maximum slope in the density. So it works well, and it compares well with the equation 12. So it's just a sanity check. But yeah, what it shows is that everything is coherent. We are like verifying first principle physics, first principle thermodynamics.
That's nice.
And yeah, we have a region which is less dense than the outer adiabat at the same pressure. Yeah, so same with radius on the right. It's yeah, it shows a bit more where we are in Jupiter, right? So
yeah, right.
even 10% of the planet. So
yes, all the actions happening. Yes, in the outer layers. Yep.
Exactly.
Absolutely.
Exactly. So it felt on the left figure that it was a small region because well, it was a log of pressure. But when you look at it in radius, well, yeah, it's a lot.
Right.
If you remember, 10% of the Jupiter radius is the Earth's radius. So we are here traveling for like three Earth radii in this plot. So big region, basically.
Very cool.
So yeah, so we were quite glad because when we like published our paper in 2019, we didn't really think about that problem. It kind of felt logical to us, and we didn't check that basically we were respecting the first principle thermodynamics. And when we verified a posteriori and expanded a lot on this, and it led to this article. Well, it does work. So that's kind of
very nice. Yes. Yeah. Yes.
If it was the other way around, I don't know.
Yeah, we probably would be here. Very
well,
good.
there are thousands of Jupiter models in the literature, so that would just be one minus, right?
At least, yes.
So yeah, so that worked, and that was pretty good. And yeah, just the end of this section 3 is interesting because it explains what is really changing well, basically the density gradient, and so the terms in equation 12 and mainly the adiabatic index. And so it changes because of the changes in the properties of the medium. And there are two properties. The first one is that H2 is dissociated with pressure. Yeah. So you are turning from molecular hydrogen to metallic hydrogen. And the second one is that you have an enrichment in helium with depth. And both of these things leads to a decrease of the degrees of freedom, so an increase of the adiabatic index. So that's thermodynamics 101, basically, for this case.
Very good. Cool.
Yeah, so that was basically what we arrived when we thought a bit about what's going on in Jupiter, how it works. So I mentioned Jupiter since the beginning, but it translates directly to extrasolar planets and even to Saturn and stuff. So that's really interesting. But the second question that we had in mind is we now have a static Jupiter profile or just a giant planet profile. But how does it work when you consider some dynamical effects?
Okay.
Yeah. So the first thing you do is you check whether you have a small disturbance, a wave that would go across your interfaces, and whether this wave will be damped or if it's well, if it gets unstable and completely destroys your model. There's no need to go through the equations because they are just orders of magnitude taken from well, the current literature or old literature. But when you go to equation 16, it's kind of interesting because it shows so it's basically the distance over which a particle could go with the typical convective velocity. So your particle is destabilized, then it goes deeper or higher up, depending on the sign of the density destabilization. And this is the distance it could travel depending on your level of superadiabaticity, so your level of overdensity and your well, the gravity and stuff like that. And so what this equation shows is that in the typical condition of Jupiter, if you just have a region that is about 10 meters, which, well, if on a region on a scale of 10 meters, you are denser than your local adiabat, then you will stabilize any perturbation.
Okay. Okay.
So what that shows is that, so you remember in our figure 1, you had this red region that was initially denser.
Yes.
And so you just need this region to be 10 meters, of size 10 meters to be sure that your medium is stable. So that's not a lot.
Right.
And in our Jupiter models, the stabilization region, the overdense region, is 3,000 kilometers wide.
Yes.
So
Yes.
there's a few orders of magnitude here.
Okay. Good.
Always reassuring, let's say.
Yeah. Well, good. Good to check that.
Yeah, exactly. Because yeah, if your medium is completely unstable, then you can throw your model at it in a way.
Yeah. Yes.
So that's a very simple view of the instability from a particle, the view we explained to understand how you destabilize a medium, etc. But that's not the proper mathematical derivation of an instability, where you have to take into account a wave of a certain wave number and see what are the conditions for the growth factor of the wave to be positive. And so this is what happened at the next section. Yeah, the conclusion of this section is just what I said, basically that you just need a very small zone to stabilize your medium. And or you would need to get instability, you would need a particle that has a velocity which is completely unbelievable. So it's statistically speaking, it can happen, but for just one particle. So
right, understood. Okay.
So yeah, so the next section really looks at whether you could have an instability from a wave. So you create a wave with a certain initial amplitude and a certain wave number, and you look at what are the conditions for your medium to stabilize your wave. There were no easy derivation of the instability criterion because our model has a stratification which changes with depth with a gradient. Right. But just with let's say a corner of the envelope calculation, you can arrive to some conclusion very, very easily. So the first conclusion is at the end of this paragraph where your mouse is, basically. It just says that rotation and magnetic tension, so basic magnetic field rotation, they can stabilize short wavelength perturbation, like 100 kilometers, but they won't stabilize higher wavelength perturbation. So you really need your medium to be stable against this perturbation. You cannot invoke physics that you have neglected before.
Right.
Basically.
Okay. Yes.
And so this is what we've done, and so we relied on the famous book of Chandrasekhar in 1961, which basically you have so much about hydrostatic or hydromagnetic instability. And yeah, what you get when you compare to that is that basically your instability depends on an integral of your density change with pressure. And you go again to the same reasoning that we had before, which is basically if you have a wide enough region to stabilize your wave, then there is no reason for your wave to get unstable and to destabilize your medium.
Okay.
And this leads to the conclusion of this paragraph, where it was basically on the right page just before evolution. What we say is okay, if you have a wave with an initial amplitude of 3,000 kilometers, which is huge for a wave in Jupiter, then you could stabilize your medium. But the question is, how do you create such a wave? And we have no answer for that.
Yeah.
So it's just kind of
driver.
Yeah, exactly.
Right.
It was kind of absurd reasoning where basically we said, yeah, this could work, but we do not see how this could exist, so this doesn't work, basically. It's an interesting figure that we have at the end is basically, if you suppose that your wave is just a slow excitation by convective motions, And given the velocity of convective motion in Jupiter, you would need 300 days to generate your wave, which is not going to happen.
Ouch, that's long.
Exactly. So yeah, so that's what we get. Then afterwards, we studied the evolution of the planet, and nice zoom in on the evolutionary path. And so it's exactly what I advocated for the past minutes. Basically, at the initial time, you have a completely convective median, the blue curve. And then at some point, you trigger some immiscibility, semi-convection, diffusivity anyway. It gets denser. You need to be denser than the adiabat initially. And so the adiabat is dashed every time. And then when the planet basically gets hotter with depth, what happens is that you have a reversal of the density gradients. And eventually you get less and less dense. And your non-convective region is denoted by the 2 stars. And you see that this non-convective region expands with time up to what we have today.
Okay.
So that's really the idea of what this mechanism. So this mechanism we have shown, it can exist in the equation. It's stable statically speaking. It's stable dynamically speaking. So we should consider it. And this is the kind of effect it would have on the evolution.
Nice.
So
very cool. Very cool.
Yeah. So that's basically. There's not much more to say in the conclusion, apart from the fact that it's from the evolution section, it's very, very difficult to provide evolution model for Jupiter because there is so much thing going on. So that's one of our conclusion. And yeah, the second conclusion is that what we advocate as well is that we don't know what is the composition of the planet when you just look at the atmospheric composition.
That's right.
Yeah. If you have any region that separates the two, then you're screwed, basically.
Very nice. Very nice.
So yeah, that was it. That was a work. Well, it took us a long time to to go through it, but we were happy with the result. And
yeah, it's a sweet little article. So Florian, thank you very much for walking us through your letter. And you hinted at it a couple of times. So I'll just push and ask a little bit. Where do we go, let's say, over the next 5-10 years? Is there a Juno 2 probe that will be going down to get composition?
I guess Juno 2, Juno 2 is a dream, but it's not going to happen.
Are there other observations that could be done, or what would be the next step? So this was, as you mentioned, laying it out in a cartoon fashion. Is there additional calculations that could be done to help verify this, or just sort of where do we go over, let's say, the next 5 years or so?
So there's 2 big stuff. The first one is that Juno hasn't still finished observing, and so it's still around Jupiter, and so we'll gather more data and have more information about what's going on, and which is nice. And what it's observing, which is really important, is the oscillations of the planet. So Jupiter, we are trying to do seismology like on Earth, but on Jupiter. That should work. And there are 3 telescopes 3 instruments that have been built in France, in Mexico, and in Japan, so that they can observe Jupiter 24 hours, 24/7. And so you get a nice Fourier transform, because basically when you have holes in your Fourier transform, you have big errors. And of course, it's weather dependent.
But, what are the names of those telescopes? Do you happen to know?
I can't remember. I know it's I know the PI of the French part and of some people, but I can't remember the name of the telescope.
Okay.
But this should lead to data in 2020, 2023. So that's going to be huge stuff.
Very nice. Yes. Yes.
So yeah, that's really the future. I think the oscillations of the planet. And you might be aware, but they have obtained oscillation of Saturn from its ring oscillation, and it leads to really interesting science. We're aiming for that.
Yeah, coupling of planetary modes and ring modes, or one from the other. Very cool. Very nice. Okay, well, it sounds like there was going to be, at least over the coming years, lots of activity on Jupiter, particularly in, let's say, the oscillations to determine the composition, which will then help determine superadiabaticity in Jupiter. So very nice, very nice. Well, everyone, that will do. I hope this made your astronomy day just a little bit better today, and we will see you on the next one. Thank you so much. Bye-bye.